Alrighty, recording should be going now. So yeah, we did 3 sections this week, right? 2.1, 2.2, 2.3.
Correct.
And we are talking about rates of change and like beginning to discuss derivatives. So do you have any specific questions, or do you want to just dive into 2.1 and start seeing what's going on?
We can dive in. It's just a little bit of a sticking point was just what do you call it? I just lost it. When you graph the derivative and you have to find like the zeros and stuff, but that's okay. In like 2.2, I think.
Yep, we can definitely go over some of that. Okay, so let's start with problem. Ooh, that's bad. That's not good. That was... Oh, never mind. Okay. Starting with problem 2, we are on page 95 in section 2.1. Okay, so use the graph in figure 2.7, which is on the previous page, to decide if each of the following quantities is positive, negative, or approximately 0, and then illustrate your answers graphically. So I'm just going to start off by sketching out this graph, this 2.7, which looks something like this. And so this is, we'll call that 5, 6, 7. This is 2, 1, 3, 4. Okay. So not exactly like perfect, but it's a good approximation of this graph, which we're going to call f of x. Okay, so we're trying to determine if the following each of the following quantities is positive, negative, or approximately 0, and then illustrate the answers graphically. So for part A, we're saying the average rate of change between f of x between x is equal to 3 and x is equal to 7. So what is it that I'm looking for?
Like, for the average rate of change, that is, you just take it's the slope for the average rate.
So what's the, like, how should I demonstrate this graphically?
Graphically?
Like, how am I going to draw this average rate of change? What I'm going to do is I'm going to say where I'm going from between x is equal to 3 and between x is equal to 7, right? So x is equal to 3 is this point right here, and x is equal to 7 is this point right here. And then the average rate of change between them is going to be...
Oh, just the secant line, okay.
Yeah, so I'm just going to connect these, and I have a line connecting my 2 points. And that is telling me what's going on here. And it's telling me that, like, on average, I'm increasing by whatever this slope is, right? And that is my average rate of change. So then what about the instantaneous rate of change of f of x at x is equal to 3? Oh, and we're going to say that for part A that this is positive, right?
Yeah.
Because m is greater than 0. Okay. What about for B, the instantaneous rate of change?
At 3 is decreasing.
Yes. So instantaneous rate of change at x is equal to 3 is we're looking at what is it happening like right here in this vicinity, right?
Yep.
And so conceptually what we're going to be doing with derivatives is we're going to say, instead of taking a point way out here at x is equal to 7, what if I pick 3.1? So we'll call this x is equal to 3.1. And if I draw a line between them, what does that kind of look like? And it's immediately like in this instantaneous like moment at x is equal to 3, it's going to be negative. So m is less than 0. So, are you okay with this?
Yeah, I was just like, I misread A. That's why I stumbled on it.
Awesome. Okay. Sweet. And conceptually speaking, just like generally, like if I were to have a point that is like here at 6, and then for instance, I'll draw what is happening here at 5. And then what's happening here at 4. Notice that each line is more and more descriptive of what is actually happening, right? Because if I have this big green line up here, I'm just saying that I'm going from x is equal to 3 to x is equal to 7, but I don't really know what's all happening underneath here. I didn't know that I'm decreasing and then I'm increasing very rapidly like this. I get a little bit of a better picture when I move over here. I get a better picture when I'm looking at from 3 to 5. I get an even better picture when I'm looking from 3 to 4. And so that's kind of why we're like counting down to see like the smallest like distance, is because the smaller the distance is between the x values, the better descriptor we get of what is actually happening. So yeah, that's the big takeaway there, I think. So let's try to do problem, let's see. Let's do problem 8. So this is on page 96. So the size S of a tumor in cubic millimeters is given by this function. S is equal to 2 to the t, where t is the number of months since the tumor was discovered. So give units with your answers. All right, so first of all, just looking at this equation makes sense, because as time increases, as months pass, then the tumor is going to be getting larger. The size of the tumor will be increasing. So first thing I do is kind of look at this equation and see what is it trying to tell me. What happens if t gets very large? What happens when t is equal to 0? And now we can tell. Okay, so for part A, what is the total change in the size of the tumor during the first 6 months? What is this question asking me for?
It's asking for the growth from time 0 to 6 months.
And how am I going to find this?
You're gonna substitute 6 in for t, so it's gonna be 2 to the 6th power.
Yep. And that is, let's see, 2, is it 64? I think it's 64.
It is 64.
Okay.
Millimeters.
Okay, and how big is the tumor? We're going from time is equal to 0. Does this mean that the tumor is 1 cubic millimeter or 0? Like how big is the tumor at time is equal to 0?
Time 0, well, going back with the information, it would be 2 to the 1.
It would be 2 to the 0.
0.
Which is equal to
1. Yeah.
So what is the total change in the tumor size?
63 cubic millimeters.
Yep. Millimeters cubed. Okay, so we've got that. So now for part B, it is asking us for the average rate of change of the size of the tumor during the first 6 months. So how do I go from what I have in problem A to what I need in problem B?
It would just be 64 minus 1 over the x-axis, which is 6 minus 0.
Yep. So I'm looking for the change in size, and then I'm going to compare that to the change in time, and delta just we're using to say change in. So change in size compared to change in time. So as you said, 64 minus 1. Change in time is going to be 6 minus 0. So we're going to end up with 63 divided by 6, which is some number.
21 cubic meters.
What was that?
21.
Are you sure it's 21?
64 minus, yep. Oh, no, hold on. I keyed it in wrong, my bad. 10.5.
Okay.
Sorry.
No, you're good. So you said it's 10.5 cubic millimeters?
Yep.
What are we missing here? One way that we could look at this is instead of saying right off the bat, like just like working through all of this, we can ask ourselves what the units are at what time, right? So here, what units am I dealing with up top here? Because this is dealing with size. So these are my cubic millimeters. That's my size. What is the units for this, for the denominator?
T is months. Millimeters per month. Millimeters of growth per month.
Yep. So what I end up having is 63 millimeters cubed over 6 months, or 10.5 millimeters cubed per month. And so that is my answer, including units. Okay, so estimate the rate at which the tumor is growing at t is equal to 6. So how am I going to go about doing this?
That's the instantaneous rate of change, so you would find the slope of the tangent line.
How am I going to do that?
Or would you do 6.001?
Yes. So I'm gonna use the same thing, delta S over delta T, and I'm gonna approximate. I'm gonna say that if I have S of 6 and then S of 6.1, I can also find S of 6.01, and that is going to be very, very similar to S. So that would be 2 to the 6.1. So 2 to 6.1 is going to be 68.59, 6.01, 64.44. Oh, I screwed that up. Sorry, I'm off. You said that this is 64. This is 64.45, 68.59. We can also look at S of 5.9 and S of 5.99. And this is really easy to do with a calculator, but not so much if you're having to deal with this on an exam. So they wouldn't ask you to estimate a rate of change like this on an exam in this exact manner, because it would be very difficult for you. So this kind of makes sense because 6.1 and 5.9 are the furthest x distance away from 6. And now we can just kind of like analyze this. We can say that if I have delta S, so if I have S of 6.1 minus S of 6, which would be 68.59 minus 64 all over 6.1 minus 6, which is equal to, and then I can go ahead and do this for the others as well. I can look at 6.445 minus 64 over 6.01 minus 6. So in short, I'm going to end up with, this is going to be 45. This is 45.9 right here. Now I'm also going to take a look at these two. I'm going to do the exact same thing. So this is going to be S of 6 minus S of 5.9. So, and then again over 6 over 5.9. So it'll be 64 minus 59.71. And then 6 minus 5.9. So 64 minus 59.71 divided by 1. So this is 42.9. And then I can look at 64 minus 63.55 over 6 minus 5.99. And so this is going to be, what, 45? So what is happening here? What is this kind of showing me?
That, well, it's growing like very slowly, like from.
Yeah, so what did I just calculate? What did I do? Like, what calculation was this?
You went to the left and right. That's a slope.
Mm-hmm.
You still did the slope like at very close, limited intervals.
Yep. So I chose very small intervals. What is the difference between, for instance, these two right here that I just starred, and these two?
The two closest are the same, like 45, and then you can tell it starts to grow faster as time goes on.
Well, what I was going for here was that if I have this line, right, that looks maybe something like that. I'm not really sure. And here is my point at 6. If I were to choose 6.1, I get a different answer than if I were to choose 6.01. So I get a much more accurate answer with my smaller interval. So these ones that I starred in yellow are the smaller intervals, which will give me a better estimation. But theoretically, I would then do 6.001, 6.0001, until the space between 6 and whatever other number I was choosing for my X value were negligible. So that is kind of where we're going with this. But yeah, so I'm estimating the rate at which the tumor is growing to be 45 cubic millimeters per month at t is equal to 6, which is a lot faster than what's happening here, right?
Mm-hmm. Yeah.
And the reason why is because if we have a graph of 2 to the x, it's going to look something like this. Mm-hmm. So my slope is very high up here and very low down here. And if I were to just draw a line, I would ignore that. But using instantaneous rate of change, I don't have to. Okie doke. Let's try some problems from 2.2, which is about the derivative, unless you have any questions.
No, I'm good.
Okay. So 2.2, we're on page, not 99, we're on page 101. And we're going to start off with problem 2 and problem 4. So I'm going to draw out these graphs. So I'm also going to sketch out something that I can use to draw these derivatives. Okay. So here's problem 4. Problem 2 looks a little something like this. This is x is equal to 3. This is -1. This is going to be -1. So I'm going to look to draw something. Maybe that looks a little bit like this. And then sorry, it's a little bit wonky, but you kind of get the idea. And then for number 4, I'm going to draw something that, if this is -1, it's going to cross. This is 4. This is bottom out. This is nope, it's crossing a little higher than that. Something that looks like this, we'll call. This will be 2, and this will be -2. Okay, so I have something that looks a little bit like this. So what is up here? What am I doing? I'm trying to graph the derivatives. What is going to be my first kind of step in doing something?
This is where I understood it in the beginning of the week, and then like last night when I was going over it, I just lost.
Is kind of very difficult for me, at least. I also very much struggle with this. I always have to break it down. So the first thing I do is I say, there are several things that I want to know, right? I want to know where I have zeros.
Mm-hmm.
So where m is equal to 0, right? The slope of the graph is going to be equal to 0. And then I want to know where I have positives. And I want to know where I have negatives. So I'm really looking for like what the slope is, right? And so I always break it down into that. So for number 2, do I have a place where my slope is equal to 0?
That's not where it crosses the, this is where I got confused. Because isn't there something when it crosses the x-axis?
We sort of. So if I'm only looking, like we'll use crossing the x-axis when we're drawing the derivative graph. But right now, I just want to think about what's happening with this problem or with this graph and just like break it down a little bit. So if I have, let's start maybe a little bit differently. What is the slope here on this side? Can you see my pen moving?
Increasing.
Yeah, so it's increasing. So that means the slope is positive, right?
Mm-hmm.
And the slope is positive from starting where we see the graph to, is it positive the entire time, or does it stop being positive at some point in time?
No, it zeros at, I'm trying to count, hold on. Where x is 1 and y at the
like
top.
Right?
Yeah.
What was that? Yeah, so this is like 2 or something.
Yeah.
So I've got this area that I'm going to kind of outline in green where it's positive.
Mm-hmm.
And then I have this area from here on over here until the end where it's negative.
Mm-hmm.
And then if I go from a positive slope to a negative slope, I have to have a point where my slope is equal to 0, my slope of the tangent line.
Mm-hmm.
And that's going to be, it's a little wonky line, but that slope is going to be right there. So I just drew that tangent line and it's flat. And that is the peak here. So when I'm graphing my derivative, so this is going to be the derivative, this graph right here. When I'm graphing the derivative, what am I graphing? What is the derivative graph going to look like? What is it going to be made out of?
The slopes of the tangent lines.
Exactly. So here at x is equal to 2, what is the slope of the tangent line of
0.
this original graph? 0. So this point is going to be 2 here. This point is going to be 2, comma, the slope at x is equal to 2 in the original, which in this case is 2, 0. So whenever there's a 0 point, which usually takes the form, well, always takes the form of like a peak pretty much, or like a valley. Sometimes there's some stuff that looks a little bit wonky, but we'll get there in like chapter 4. But what we're looking for basically is we're looking for the point at which the tangent line is equal to 0, and then we say that that's 0 on this derivative graph right here. So what is happening beforehand?
It's increasing.
Yes, so this is positive. What that means is that from x is equal to, or yeah, from like infinity up until 2, right? I'm going to be only dealing in the positive numbers. Because if I were to have a point down here, that would indicate that this is a negative slope. So I know that I am coming in from positive numbers. Next, I need to ask myself, where along this green line is it most positive? Is it more positive, like is the slope larger at this bright green point down here, or at this green point right here? We'll call them
at the upper green point.
It's more positive at the upper green point?
Oh, actually, no, the lower green point, sorry. Because the upper one's approaching 0, so it would be...
Yep. So if I sketch a line here and I sketch a line here, this one is going to be more positive, and this one is going to be less. So I know that I'm moving from a point of being more positive to a point of being less positive. Okay. So the next thing I need to ask, is this happening at like a consistent rate? And I can tell you right now that, yeah, it is. And the reason I know that is because I'm working with a parabola function right here. And parabolas, when you take the derivative of them, we're going to learn this later, but if I want to take the derivative, this is derivative of a parabola function, the answer is going to be a linear function. So I know that I'm going for a linear function here, and even just kind of looking at this, I can say that it's a parabola. It's going to be going at a consistent rate. It's going, like the positiveness of the slope is going to be decreasing at a consistent rate as it approaches 0. So I feel pretty confident in drawing this right here. And then I'm going to do the exact same thing over here, right? What is this going to look like, the rest of this derivative graph?
Well, it's decreasing at a higher rate at the other, so it's going to go straight through. So it's going to continue the linear.
Exactly. Yeah. Because at this point, it is less negative. And at this point, It is more negative. So less negative when x is equal to like 2.5, more negative when x is equal to like 3, right?
Mm-hmm.
So that's how I end up with this line coming down here. And as I said earlier, later on we'll be able to say algebraically like why that's the case. But for now, we're just gonna kind of break it down into where is it positive, where is it negative, and then break it down into which, like if I compare 2 points, which is more positive and which is less positive. Okay, let's try again with number 4. Okay, so do I have any points where my slope is equal to 0?
Yeah. Kind of like between -3 and -2.
Mm-hmm. So we'll call that -3.5. And the other point is going to be at like
Trying to count here.
2.5 maybe?
Yeah.
Okay. So I'm just going to go ahead and mark those down right away because I know that that is going to, like, it's going to cross the x-axis here because at these points I'm transitioning from positive to negative. Okay. So what's next? Let's just move from left to right. In this stretch here, from the edge of the graph to this 0 point, is it positive or negative? Is the slope going to be positive or negative?
Negative.
Okay. And I know that I can't switch from positive to negative without going through 0 first. So that's why I can break it into from 0 point to 0 point. Is this going to be positive or negative? The slope.
That's going to be positive between the 2 0 points.
And then from this 0 point to the edge of the graph, positive or negative?
Negative.
Okay. So I know that I will have something down here, and I'll have something down here, and then between these points, I'll have something happening up here. So I know kind of generally where I'm going. So I'm, you know, you can kind of see a shape that's beginning to emerge. All right, so is it more positive here at x is equal to -4 or at x is equal to -3, or more negative, excuse me? Where is it the most negative?
At -3.
Is it the slope more negative at -3? If I were to draw this slope versus if I were to draw this slope.
Oh, okay. No, -4.
Yep. Which means I am approaching 0, right? So I'm going to have something that looks like that. All right. So now I'm going to ask kind of the same thing. If I have this point at, so at this would be 3, and then I have this at, I don't know, 3.5, which is more negative?
The one at 3.5.
Yep, which means that I'm moving from, if that's 2.5, then I have something that's negative at 3 and then more negative at 3.5. So I can kind of, I shouldn't have sketched this in peach. I should just sketch. So I have something that looks like this. Okay, so I broke down the negative portion, right? Now I need to break down the positive portion. Somehow have to be able to connect these 2 portions, right? Without crossing the x-axis again. Why can't I cross the x-axis again?
Because it's positive.
Exactly.
So it can't be a negative. Yeah.
So I can't go down into this negative because that would indicate that there's another 0 here, and there's not. So what can this look like?
I'm sorry, what? You cut out.
Oh, that's okay. What can this look like?
It'll be a parabola.
Yeah. I'll have a hump.
Yeah.
Because it goes from this is less positive to more positive, and then there's a point here where it's the most positive, right? And this is, later on we'll learn more terminology, but for right now we'll just call this the inflection point. Well, that's what it is. You'll learn about that later. And then it goes from being, this is the most positive slope, and then it gets less positive, and then up to the 0 point. So this is this point right here, that's the inflection, where it is the most positive slope. So we end up with something that looks like this. And this is actually not going to be a parabola. If we have a function that kind of looks like this that we've drawn, we can kind of, obviously we can't really, because there's, this is where the graph cuts off, but it does look pretty periodic. So we can assume that it's going forward. So we can assume that it's going to loop around like that.
Okay.
Because later on, we're going to determine that the derivative of a periodic function is a periodic function. So although this might not look quite periodic like it is right now, we can kind of draw like a little bit of a curve there and a little bit of a curve there, because we know that it's periodic and it's going to start coming back up. However, they cut off the graph before we could really see that, which I think is unfortunate, because it implies that this type of graph will yield a parabolic derivative, which is not true. Okay, do you feel a little bit more comfortable with this type of stuff?
Yeah, now that I kind of have like a breakdown on how to break it down a little bit better, yeah.
Mm-hmm.
Like a step-by-step process to use, yeah.
Okay. Do you want to try another one? Do you want to try maybe
we could try another
one? Do you want to try maybe like something like problem 8?
Sure.
Okay. So we're given a graph that is a parabola, and that graph is f of x, and it asks us to estimate a variety of like numbers. And so this is just kind of like looking at a graph and saying, this is like what I can pick out about this graph. So here's our parabola. This is about, this is 1, and this is 3. So that's 2, 1, 4, 5, 6. Consider it goes up. 1, 2, 3, 4, 5, 6. Okay. So what do we think f prime of 1 is? What is this asking us for? What is f prime of 1?
Tangent line at 1.
Mm-hmm. Or more specifically, the slope of the tangent line at 1.
The slope, yeah, sorry.
Yeah,
1, that's the rounded point of the parabola, so it would be 0.
This is an x value.
Oh, okay. Oh, yeah. So 1 for x.
So we have a point that's like way up. It should be at 1.5 actually. So my scale is wonky. So this is 5. So, what do you think?
It would be decreasing.
Mm-hmm. So we know it's going to be negative.
Mm-hmm.
And I'm kind of looking, so like if I go from 1 to, it's kind of hard to see with this really sketchy thing that I've drawn out here, but if I go like up here, and this can be like 1, or not 1, this would be like 0.75, the 0.75, like 6, right? And then if I were to go down a little bit, I could have like 1.25, comma 4. So I could kind of like figure out, I could say if I have like delta y over delta x, I could estimate that using the graph, right? So this would be an average rate of change, but I could use it to approximate an instantaneous rate of change. So I'm going to do that. I'm going to say I have 1 minus 0.75, or rather, that's wrong. I'm going to say I have for delta y, I have 5 minus 6, and then I have 1 minus 0.75. So this is going to turn out to be negative 1 over 0.25, or negative 1 over 1 over 4, which I can call negative 4. So I'm going to estimate this to be about negative 4. And the way that I did that was I just, picked a point and went with it to find the average rate of change. And yeah. Okay. What about for f prime of 2? What are we looking at here now?
For the f prime of 2, it's still negative. So then you would repeat the same process you just did, where you would take another approximated point.
What point would you pick?
2.25. Wait, hold on. Yeah, 2.25.
And then what is the y value there?
Um, 1.5, kind of, maybe. I'm trying to estimate. It's really hard.
Yeah. I would say it's a little bit closer maybe to like 1.75. I think it's closer. It's not quite all the way to 1.5. So we can call that 1.75 maybe. So the way that we would set this up is we would say this is 2.25 minus 2 over the 0.2 comma 2. So this would be 1.75 minus 2. And this would end up being 0.25 divided by negative 0.25. So this would be negative 1. So again, we have this average rate of change that we've used to approximate. Kind of draw those lines in there. So yeah, that is that. Now, what about for f prime of 3?
0.
Yep. We know that our tangent line looks like that. Don't really have to worry about it. And then we would use the exact same method that we used for 1 and 2 to find f prime of 4, which is going to be pretty much approximately 1, I think, because this is going to be positive now. But it's not really, I mean, you just walked through it for the last one. We could do the calculations again, but
don't they mirror the other side? So it's kind of.
Yeah, they do. So it's kind of redundant. So this is going to be approximately 1. And then once we get to 5, it will be approximately 4. Just the positive versions of what happened up here. So yeah, again, this is just kind of like breaking it down into smaller pieces. Okay, do you want to tackle some problems from 2.3?
Sure.
All right, so this is interpretations of the derivative. This is okay, so you guys covered some Leibniz notation. You guys covered what else in this section? Approximating tangent lines. Let's start with number. Let's do number 2. So the cost C of a steak in dollars is a function of the weight W of the steak in pounds. So for these problems, we're asked to write the Leibniz notation for the derivative of the function and include units. But let's first start by figuring out what this function could be. So what is going to be kind of my y analog versus like my x analog? Like if I were to write something like f of x, right? I know that I have a function of a variable x. So what is this going to look like?
C equals f of w.
Very good. I could also just call it c of w. But exactly. So if I take the derivative of this in Leibniz notation, what is that going to look like?
It's going to be a d of c over d of w.
dc dw. Exactly. So another way that I could put that is
Dollars per pound.
yes, and it is going to be unit-wise dollars per pound. Okay. So the important thing to take away from this, I think, language-wise, is I'm taking the derivative with respect to w. If I see anything that looks like this, d variable, I am taking the derivative with respect to this variable. If I see something like this, I can read that aloud in my head as saying I'm taking the derivative of c with respect to w. And that's just kind of how Leibniz notation reads. So yeah, let's do number, what about number 4? Let's quick do that. Same process, I think. An employee's pay P in dollars for a week is a function of the number of hours worked H. What does this function look like?
P equals f of h, and then it would be d of p over d of h.
And this just means the derivative of P with respect to H. So yeah. And what would the units be for this?
Dollars per hour.
Yep. Okay. All right. Let's try, I don't think I wrote the page number down. I'm going to be on page 109 now. Let's try number 16. So the average weight W in pounds of an adult is the function W is equal to F of C, which is, C is average calories per day. Consumed. So Interpret the statements. F of 1800 is equal to 155. And F prime of 2000 is equal to 0. Okay. I will start off right away saying I don't like putting this in terms of F. Like I did earlier with the stake one, the cost and the weight, I would prefer to write this as W of C, so that I know that I have a function weight which is dependent on calories. It's a function of calories. It just makes it clearer to me to like write it down like this, so that I know that this is the function that I'm working with. So I'm gonna change this to make this more clear, especially when it said F prime. I was like, okay, that seems useless, because what I really want to know is, the rate of change of the weight, not the rate of change of F, which is the weight. It just seems like an unnecessary step to me that stresses me out. So I'm going to write it as W of C. So what does this in the purple mean? Like, what is the interpretation of this?
Hold on one second. The average weight of a person who consumes 1,800 calories a day is 155 pounds.
Yep.
Sorry, that defies my logic.
Okay. Now, what about this in the green? W prime of 2000 is equal to 0. What does W prime mean?
It's the instantaneous rate at 2,000 calories.
Instantaneous rate of what? The rate of change of what?
Change.
But what is changing?
The weight?
Mm-hmm. And so our rate of change of weight at 2,000 calories a day is 0. What does this mean? So if I'm a person and I weigh 160 pounds and I eat 2,000 calories a day, what does this mean about my weight?
It's not going to change.
Exactly. Exactly. All right. So what are the units of, what are the units of F prime of C, which I'm going to call W prime of C, which is dW dC. So this is the rate of change of weight with respect to calories. So what are these units going to be?
Pounds per calorie? Or
so pounds, like change in, like the change is pounds per calorie per day. So we're going to kind of like keep this as like one kind of set, because our C is already in calories per day consumed. Okie doke. Does that make sense?
Yeah.
That was very tentative.
Yeah. Well, no, like I understand what they're trying to say, but in my opinion, just with my background, it's a horrible example.
Yeah.
Yes.
But the math makes sense, right?
Yeah.
Okay.
Yeah. the math and how to read it, and that if
Yeah.
you consume 2,000 calories per day, you're going to maintain your current body weight. There's going to be no change.
Yeah. Of course, this is, not a perfect example, but we also have no idea what this function looks like. Like this function could be, really super long and very, very convoluted. Should probably depend on more than one variable, but I guess that's just not how they wanted to write it. Okay. Let's also try, sorry, I'm looking at problems. Okay. Let's take a look at problem 26, which is a subset of 24 through 27, where we're looking at the weight of a fetus as a function of age. So we have this graph, and this graph looks like this. Yeah, it's a little bit more curved than that. Looks like that. Okay. We have this graph. This graph looks like this. This is about 16. And this graph we're calling G of T. Okay, and this is 3, 2, 1. All right. So, and this is T, age of fetus in weeks. And this is weight in kilograms. All right, so is the instantaneous weight growth rate greater or less than the average rate of change of weight over the 40-week period? So what this is kind of asking us is, first of all, we need to figure out what the average rate of change of the weight is. Because it's asking us to compare an instantaneous rate of change to an average rate of change. And we have neither right now. So let's start off by finding that average rate of change. And I'll do that in the blue. What is that going to look like?
Average rate of change is going to be increasing. So you would just pick 2 points on the line and find the slope of the secant.
Yep. So I just pick 2 points, right? And then I draw a line between them. And that is my average rate of change, the slope of that line. What 2 points am I going to pick based on what the problem is asking?
Between 20 and 36.
Or
want to capture them, so would you go like 19 or 16 and 40?
I'm not using average rate of change to estimate right now. I'm trying to compare an average rate of change to an instantaneous rate of change. So like the way that this problem is worded is a little funny, but is the instantaneous rate of change greater or less than the average rate of change? So it's asking me to compare and it's asking me to do that at 2 points. It's asking me to do that at t is equal to 20, and it's asking me to do that at t is equal to 36. But in order to do that, I need the instantaneous rate of change at t is equal to 20, and I need the average rate of change of what?
The secant between those 2 points.
Which 2 points?
Or t is equal to 20 and t is equal to 36.
Not quite. That would look something like this. And that's not what I'm going for. I'm looking to compare the average rate of change over the 40-week period.
Oh, okay.
So this is going from t is equal to 0 to t is equal to 40.
Okay.
So I'm comparing the average over 40 weeks, and I'm going to draw that using this straight line tool because I can, to the instantaneous rate of change at these various points. So for part A, I have my average rate of change now. What is it going to look like when I have something, this is t is equal to 20, right? And that's 20. What does this line look like? What does the tangent line look like?
It's positive, but not as steep as it's going to be at 40 weeks.
Yes, very true. So I'll also do this over here. Instantaneous rate of change at t is equal to 36. So 36 is going to be up here-ish, and it's going to be much more positive, as you said. It's going to be something that looks like this. So now we're just going to eyeball it. This looks less positive here at 20 than the average rate of change. It looks a little bit like if I were to extend this line, it might connect with this blue line at some point in time. You can kind of see that they're kind of converging if I stretch it out. And then I have this peach line here, which definitely would converge on the blue line. So here I'm going to say the instantaneous rate of change, or the slope of the tangent line at x is equal to, or t is equal to 20, is less than the average rate of change over 40 weeks from t is equal to 0 to t is equal to 40. So what I'm saying here is that comparing the average rate of change to the rate of change at week 20 is not going to be the most accurate, because at week 20 it is growing slower than it would if we just looked at the average. Then I can also say it would not be great to compare the rate of change at week 36 to the rate of change, the average rate of change, because the rate of change at t is equal to 36 is greater than the average rate of change. So again, from t is equal to 0 to t equal to 4. Does that kind of make sense?
Yeah.
Okay. So this question is just asking us to say, is the instantaneous rate of growth rate, the instantaneous rate of change, greater or less than the average rate of change of the weight over this 40-week period? So here in this green, I can say the instantaneous rate of change is less than the average rate. And then here in the peach, I can say that it's greater than. That's a really sloppy looking star. Okay. Any questions?
No, I got that one.
Okay. This is just kind of, it's getting to be a lot more conceptual, but just kind of always break down, break down what's happening. Yes. Just for kind of practice's sake, I'm going to erase a little bit of this graph up here, but is there a place in this G of t graph where G prime, or where G of t is equal to, or the slope of G of t is equal to 0, where G prime would be 0? Is there a point where that case?
Looking at the graph, yeah, but that's at the point of conception.
Yeah. It's also pretty much flatlined. I wouldn't, like, if I were to draw a derivative of this, it would be flat from basically 0 to 12 weeks. That's like a solid nope. That's a solid 0 for me. So if I were to sketch out this, it would look something like which looks very, very similar to this. And that is to be expected when you have an exponential function, because as we'll learn later, exponential functions, when you take their derivatives, they yield another exponential function. And by exponential, I mean this is something like e to the x or 2 to the x or something like that. Something that's not like x to the third. So I have a function that is growing exponentially, and if I take its derivative, I'll get a function that is growing exponentially. So that makes sense. So that's something that you'll see later on. So yeah, when it comes to doing stuff in 2.2 and like recognizing these kind of graphs, there's a lot of patterns that you'll pick up. Later on, when you're doing the algebra form, you'll pick up patterns. But it's good to, when you're like drawing these graphs, to kind of see what the patterns are. All right. Do you have any questions? 2.1, 2.2, 2.3? Any of that?
No, I think I'm good right now. I'm just going to practice breaking down the graphs and taking and converting a graph of a function to the derivatives. And now that I have like a step-by-step example, it's just going to be practice.
For sure, for sure. Yep. That's really all I have for you today. If you have any other questions, feel free.
Let me just go through my homework and see if I had anything marked, because usually that's what I do as I'm going through the assigned.
No,
I got that. Oh, from 2.2, number 29.
Okay.
I'm probably going to understand it now that you explained it, but when I was going over it.
Okay. So match each property, A through D, which is given, with one or more graphs of the functions. So this is problem 29. I'm on page 103. And I am going to say I've got this like property, I guess it's what they call it. F prime of x is equal to 1 for all 0 is less than or equal to x is less than or equal to 4. So break this down for me. What does this mean? Without even looking at the graphs right now, what does f prime of x is equal to 1 mean?
Wherever x is 1. No. Like, I know it's a straight line. This is where I get confused, is like trying to verbalize it.
Nope, that's okay.
It's just a consistent, it's not going to change because it's equal to one constant.
Yeah, so what is f prime of x?
It's the slope of the tangent line.
So I'm just going to say m is equal to 1.
Mm-hmm.
And it's consistent. It's the same for all 0. So if I were to have a graph that looks like this, and I had, I could have any number of lines. I could have a line that looks like that. I could have a line that looks like that. I could have a line that looks like this. but m is equal to 1 for all of these, right? And it's consistent from x is equal to 0 to x is equal to 4. So any one of these lines would be an appropriate answer for this question. So for this question, instead of looking at the graphs right away, I kind of just took a look at the equation. So now if I were to go back to the graphs, what graph fits this function?
With what you drew, the third one.
Yes, so number 3 is going to be the answer here.
But I think the book, maybe that's where I got confused. Unless I read when I was checking it. Maybe I was looking at the wrong answers, that's why I got confused. Hold on. Just give me 1 second.
Okay.
I'm just going to the solutions. Maybe that's where I got confused.
Yeah. It's okay. So this is, I think the issue with number 29 is, did they draw f prime of x or f of x? They didn't label it.
They just gave the 4 graphs.
Yeah, this is a poor question.
Because it answers. No, maybe I looked at it wrong. Maybe I looked at the wrong answers. That's why I was getting frustrated. Because I thought it was, because 1 is 1 over 1, and for some reason, I thought it was 4, like looking at how the graphs were, because the axes go from 0 to 4.
Yeah.
And it's still a straight, and it looks like, but that's at 2. That's where, okay. Maybe it was just, I was frustrated and it was like towards the end of when I was doing my homework.
That's fine. But yeah, so basically what we have here is we have this, if I were to draw the derivative graph for this, it would look like this. So here in the pink, this is f of x, and then this is f prime of x, which I'm going to rewrite in the light blue. F prime of x. F prime of x is equal to 1.
And that's what I have, but then if you look at the answers, it has graph 3.
Yes. So the issue with the question is that it's poorly labeled. I have a graph here. This is a derivative, right? This is my derivative graph. It wants me to find what actual function correlates
with the derivative.
Yeah, so they give you this. They're not asking you to draw like a line and say, I have this graph, f prime of x is equal to 1. It's a straight line, flat line. They're asking you pick out which function it could be. So the function that it could be is this one, where the slope is equal to 1. And if I were to take the derivative of this, I would end up with a graph that looks like this flat line here. So let's take a look at problem B, and we'll kind of do the same type of thing. Here we have f prime of x is greater than 0. And I don't know why they say for all 0 is less than or equal to x is less than or equal to 4 for these first two, and then not for the second two. Oh, I see why. Never mind. Because they give you an x. But so we'll write that down. For all 0 is less than or equal to x is less than or equal to 4. Okay. So let's take a look at the functions and see what options we have. What is your gut kind of telling you on this one?
For any, it's going to go from 0 and it's going to increase until it hits 4. But then after that, you don't know because it stops at less than or equal to 4.
We just know that it's increasing from 0 to 4. And that's all we know about that. So this is 3 up here. This is 1, this is 2, and this is 4. Which, for number B of the graphs, is increasing over the entire period from 0 to 4, always increasing.
2. Oh, always increasing from 0 to 4 is 3 because it's linear.
So 3 is always increasing. And another way that we could look at this is if we were to draw these derivative graphs. We could sketch them out so that they looked something, for number 1, it would be a flat line at 0, right? Because the slope of number 1 is 0. What would the derivative of number 2 look like?
Well, it's 0 at 2. And it's so wouldn't it be a straight line through 2 approaching?
And then what about for number 4?
For number 4, it's 0 at 3. And
is it increasing from 1 to 3?
Yeah.
Okay, so it's in the positive area and then down. Okay, so we could ask which one of these graphs, I have number 3's up here, and then I have 1, 2, and 4's right here. Which one of these graphs is always greater than 0? Well, we can see that number 1, the derivative graph, is 0 for the entire period of time. For number 2, it's not always greater than 0. For number 3, it's not always greater than 0. But for number 4, excuse me, but for number 3, it is, because it's equal to 1 the entire time. Okay. Then for part C, so we were right about number 3 being the answer to both A and B. For part C, it's asking us f prime of 2 is equal to 1. So one way that we could do this is I just drew in the green and then up here in the blue what all of these f prime graphs look like. I can just go ahead and pick like exactly where. Here is f prime of 2, or this is 2. So this point on the graph is f prime of 2. Here is 2. Here is 2. And then here is 2.
So it'd be the last one, because it's always equal to 1. No, the next one over to the, well, that's f prime equals 1.
Yes, so number 3 would be a valid answer because f prime of 2 is equal to 1, right?
Yeah.
Because f prime of anything in that graph is equal to 1. So f prime of 2 also equals 1. Here, this could also be another correct answer, number 4. It looks to be approximately 1 to me. We could find exactly what the slope is at 2. My guess is it's going to be approximately 1. And I'm pretty sure that's what the answer key says. Yep. Okay, so finally for part D, we're given find out where f prime of 1 is equal to 2. So we're going to do the exact same thing that we did in this last one. We're going to go through and say this is 1, this is x is equal to 1, This is x is equal to 1. And this is a little wonky, but if I said that that was 1, then I could put this up here and say this is 1, 2. So, what are potential things that we could, what are potential graphs that work here?
2.
Yep, 2 works. And what other one?
4.
Mm-hmm. Exactly. Does this kind of make more sense?
I'm still confused over this one. I just don't know what.
Okay. Do you not know what's going on now, or do you not know what had you confused earlier?
I don't know what had me confused earlier, and it's just because, I don't know. Hopefully I don't see this on the test.
I think this question is really poorly worded, so I would hope that they didn't put something like this on the test. But do you get like what's happening? Like, did you follow how we figured all of that out?
I followed it, but I'm still I'm still looking. So I get 1/1 is like over 1 up 1. And then how the function is just a straight line because x always equals, the y is always equal to 1.
Uh-huh.
The derivative. I'm just looking at them and like looking again. So it's
Okay.
decreasing.
Yeah.
I just think maybe this was just a bad question.
Yeah, it is. It is a bad question. My first step when solving this question, I kind of set you up doing this and like walking through like what this might look like. But if you're given a question like this where you have 4 derivatives and you're going to need to find them all anyway, step 1 should probably be to find, this is f prime of graph number 3. This is f prime of graph number 1, number 2, number 4. And like explicitly write out what's happening here. It's also worth noting, you can't really see it in my drawing, but this is like a wider parabola than what's happening over here, right? So the slope for this is going to be smaller than the slope for this, which is why we can have the point 1, 2 and 2, 0 here, and the point 1, 2, 2, 1, and then 3, 0. Is that this slope is different. And that's because this parabola is shaped differently.
It's kind of shifted. And you can see that between 2 and 4 too, that 4 starts at x is 1, whereas 2 starts at the origin and looks narrower.
And we could theoretically put this down, like continuing even further. But yeah, so there are a lot of issues that I think I have with this problem. I wouldn't dwell on it too much because you seem to have gotten most of this other stuff. But as long as you can recognize what like if I have a parabola and I take its derivative, I get a straight line. As long as you can remember that, I think that this problem, approaching this type of problem, should be pretty fine for you.
So here's a question, and I hope, so really what they did is they gave us functions in the graphs, and then we just had to convert them to the derivatives. Okay.
And just pick up
maybe
which
had they
ones
labeled
match.
those as,
yeah, this is a badly written problem. I would not dwell on this problem. They did. Okay. There were a lot of things that if I were in charge of editing this book, I would change about this problem. So.
Okay. Yeah, and honestly, I was looking at my schedule, and a lot of my anxiety has decreased because it looks like the midterm is the week after spring break. So.
Is it?
Yep.
Wow. That's good and bad, I guess, too. I know somebody who has a professor who purposely schedules 2 midterms over the course of a spring semester. The first midterm is the Monday after Super Bowl Sunday, and the second midterm is the Monday after spring break. And he schedules it like that every year just to screw with people. And I know, it's just like, why would you purposely be that rude? But I guess whatever.
Like the first time I went to college, like I'm getting, like my anxiety is decreasing over calculus. I think I still have residual one, it's calculus, but it's pretty much algebra again. My first go in college, the professor said 2 things. 1, if you need to have a job while you're in college, you shouldn't be in college. 2, if I find out you're going to the, and he goes, and if I find out you're going to the tutoring center for calculus, I'm going to call on you every day in class because that means you should know it if you need help with something. Because at that university, they would rotate the upper level math professors who taught the more advanced courses. And it was like punishment for them that every so many semesters they had to come down and teach pre-calc.
The worst. It's like, that's the worst. I don't know. Having a teacher who doesn't care about teaching like that is very frustrating.
And it was beneath him, and it was just in like college, and I'll let you go. It's just, I try to remember I'm a student and I need to learn, but at the same time, it's also customer service anymore. It's like, why would you screw with your customer?
Basically, I mean, if we're paying to go to school.
And honestly, there's a lot more quote unquote non-traditional students than there are traditional students anymore. Because I went in and I have a lot of work experience, but then I flatlined when I was told, oh, we want you to be the shift manager, but we're bringing in people with bachelor's degrees on paper and we're giving them an average of $7,000 more a year just because they have the degree. I had 3 years of experience and exemplary evaluations and a track record of successful validation processes, but because I did not complete a 4-year degree, and I was in the scientific field in tissue banking, they said I couldn't have the $7,000 to start out on a level playing field.
It's crazy how much it's just basically a requirement to like enter a field with a bachelor's degree nowadays. It's shocking.
But yeah, I still have, like, I'm getting better, and it's just getting back into it. And I think, I don't know, maybe, I don't know, do you come across a lot of people who have anxiety over pre-calc or no?
Calculus is an extremely anxiety-inducing subject. That is for sure. To be honest, I actually had like a test dream last night about Calc 2 for some reason, which I have taken and passed, and it's over in my life, but I'm like still having like residual fear about calculus. And I like teach it. So it's not like, it's just a scary topic. It's a complicated topic. It's a topic that a lot of people struggle with. And really it's not something that you should be scared of, but it is something that a lot of anxiety gets attached to. So I've seen a lot of students who come in and they're pretty worried about this class, or about the other class that I Gsg for, which is also a Calc 1 class. And they just get very, very stressed.
Well, what stresses me about this, and I understand looking at it because I also did quality assurance and environmental control, is the fact that there's absolutely, like, most tests anymore, it's either open book or non-proctored, or even if this is proctored and you have to scan your room and et cetera, you can't even have like